This is the second lecture on quantum mechanics in 1D. In the earlier class, we have studied the one-dimensional, infinite, rectangular, asymmetric potential well. That is the potential well that we considered in the last class where extend from 0 to A. Instead, we have to consider a symmetric potential well. That means we have chosen the position coordinate in such a way that the potential well extends from plus A to minus A, the same potential of with A, but the extent is from minus A to plus A, because the system had a symmetry. If we consider the potential like this, and if we fold this by along this line, which passes through the midpoint of the well, we see that nothing changes. That is, if we choose the coordinate system, position coordinate system at the middle of the well, and if we replace x by minus x, nothing changes. So this is the potential is an even function if we choose it in this way. That is the way we have chosen the origin of position coordinate at the middle of the well, so the potential is an even function. This is a symmetry of the system that was there, but in the earlier class we haven't considered this. Today I shall first derive this one and see what extra information do we get by choosing a potential well which exploits the symmetry of the problem, and then we will go to the general theory. So the wave function is 0 as usual. Wave function is 0 here, wave function is 0 here, and wave function is non-zero in the well. So for x less than equal to plus L, instead of a by 2 I write L, we have, and with L is equal to a by 2, we have minus h line square by twice m d2 phi dx d2 psi dx2 is equal to e psi, where psi is the time independent Schrodinger equation, solution of the time independent Schrodinger equation, which is, as we have done in the last class, is this, with k square is equal to twice m e by h line square, and k is a real quantity. The solution of this is x of a is equal to a sine kx plus b cos kx. This up to this we have done exactly the same in the last class. Now the boundary condition here is BC is phi at minus L is equal to 0 is equal to phi at plus L. If we apply this condition, we have phi at L is equal to a sine KL plus b cos KL is equal to 0. That gives you tan of KL is equal to minus b by a, with the assumption that a not equal to 0. Whenever we are dividing a quantity by something, it is assumed that it is not 0. And phi at minus L is equal to minus a sine KL plus b cos KL is equal to 0. This leads to cot KL with the assumption that b is not equal to 0. If we multiply these two equations, we should get that plus 1 is equal to minus 1. Because this is on the left hand side you have tan KL times cot KL, which is 1, and on the right hand side this cancels out. So we have arrived at an absurd situation. This is an absurd situation. The only assumption that we have made is that in the first equation A naught equal to 0, and in the second B naught equal to 0. This absurdity has arisen from this assumption. So we conclude that A and B, both the expansion coefficient, the constant of integration, cannot be non-zero are equal. If A is equal to 0, then B is not equal to 0, and vice versa. That is to say, the equation either comprises of sine term or cos term. So the conclusion is that both A and B cannot be equal to 0 simultaneously. So the alternatives are one is A equal to 0, B not equal to 0, and second is A not equal to 0 and B is equal to 0. If we choose the solution in this form, then only this part survives. So the solution is even. Solution is even. And if we choose the solution in this way, the solution is odd. Because sine function is an odd function and cos function is an even function. So the conclusion, immediate conclusion, is that the solution we cannot have solution in this fashion if we exploit the proper symmetry of the system. The system has a reflection symmetry about the center of the well. So if we choose the coordinate system which exploits this symmetry, the solution again breaks down into two categories. One is the even family, other one is the odd family. Let us move with it. So first we consider the solution. We decouple the solution into two parts. One is this, and this is, so the solution is this: phi even of x is equal to b cos kx, and phi odd of x, we first start with the even category. So the solution is phi. Now the boundary condition is phi even at L is equal to 0. This is equal to b cos KL is equal to 0. For non-trivial solution, we have cos KL is equal to 0 is equal to pi, with n is equal to 0, 1, 2. 0 is included, because when n is equal to 0, it is simply pi by 2. So we get kn even. Since it comes from even solution, we use a superscript even. So this is equal to 2n plus 1 by 2l pi. The corresponding energy values are, and we see that this is 2l is equal to a, so this is 2n plus 1 by a pi, and the corresponding energy values En even is equal to pi square, sorry, h line square k square by 2m. Now it becomes, this actually becomes kne square, kne whole square. So this is pi square h line square, this pi square comes, and in the denominator we have 2ms square 2n plus 1 whole square. If you remember the definition of epsilon, the quantization unit we used for the asymmetrical, this is epsilon, this in terms of epsilon it is 2n plus 1 whole square, where epsilon is pi square h line square twice ms square, whose value we have calculated for 4 alternative cases in the earlier class. And now come to the odd solution. And the boundary condition is sex. For non-trivial solution, sine of n pi. So we get kn odd is equal to n pi by L. We write it as 2n pi by 2L, which is equal to 2n pi by A. So the energy coming from the odd solution, the restriction over n is 1, 2, etc. 0 is excluded. So in terms of epsilon, this is epsilon 2n square. And so far the normalization is concerned, the normalized wave function, it is a trivial task, and I am not going to take it up. This is 2 by A cos kn is this much, you see this is the odd number and here is the even number. So whenever you are talking about even solution, the argument is odd, and whenever we are talking about odd solution, the argument is even. And furthermore, we have applied boundary condition only one end. You need not to apply the boundary condition on the other end, because this was applied and we have decoupled the solution into two branches. If we apply the boundary condition on this, you will again land up with the same equation. No new quantity, no new result will be obtained. Now this is the energy expression. If we recall the energy expression for asymmetric well, En was epsilon n square, where n could have 1, 2, 3, 4, etc. If we draw the energy level diagram of this is zero level, this is epsilon, then 4 epsilon coming from n is equal to 2, then 9 epsilon coming from n is equal to 3, then 16 epsilon coming from n is equal to 4. This is the energy. This is for asymmetric well. If we consider the symmetric well by the side, this is the zero level. This is the epsilon energy comes from this. When if you put n is equal to 0 from even state, it is n is equal to 0 this energy level is here also, but it comes from n is equal to 0 of even state. Then the 4 epsilon, if we put n is equal to 1 here in the odd state, we get this. So this comes from n is equal to 1 of odd state. Then we come to 9 epsilon. If we put n is equal to 1, then this is n is equal to 1 with even state. And finally, if we consider this is 4, so n is equal to 2, n is equal to 2 of, n is equal to 2 of odd states. And the next one is obviously 25 epsilon, which will come from n is equal to 2 of even state. If we put n is equal to 2, it is 25. So the conclusion is that the energy levels of an infinite potential level comes alternatively from even and odd states. The ground state energy is an even state. Ground state corresponds to an even state. What does it mean by even state? By even state, the property of even state is that phi even of n of minus x is equal to plus phi even of n of x. This is the even state property. And the odd state has the property so we see that the ground state energy, ground state belongs to an even state, and the other states are alternatively coming from even odd, even odd, even odds. this is the general property of every system for which V has a definite parity. That is, if we replace V by minus V, V by V of x by V of minus x, if the potential remains the same, then the solution for the system can be decoupled into even and odd category, and the ground state corresponds to an even state. So we return back with the general theory. What is the what should be the wave function of the property of the wave function when the potential has a mirror symmetry? Or let me first discuss what do we mean by parity operation. Then I shall come to this parity operator of quantum mechanics and its eigenvalues, etc. Consider we have a coordinate system, three-dimensional coordinate system, and we have a point, position vector r, and some physical quantity is, we have a position vector, say r is the position vector, whatever coordinate system we are using. If we get a reflection of this r with respect to origin about a plane which is perpendicular to r, we get the position vector this minus r. So the operation that transforms plus r into minus r is called the parity operator. So the parity operator is this. If we call parity operator r, so r when operated by parity operator p becomes minus r. Let us see what happens in a pure simple coordinate system. In 2D Cartesian, this is position vector r having coordinate xy. When we will take this mirror image, we will have the point minus x minus y. So for this case, xy transforms to (2D polar). This is the point r theta. When we take the reflection, r remains the r because it is the radius vector and positive quantity, and theta changes by this amount. So r theta changes to, under parity operation, changes to r theta plus pi. As a check, x is equal to r cos theta. In the third quadrant, cos theta is negative, and y is equal to r sin theta. Again, all sine, tan, both sine and cos are sine and cos are negative in the third quadrant. 3D Cartesian. This is r, this is minus r. Obviously, here we will have x, y, z will be transformed to, under parity operation, minus x, minus y, minus z. Cylindrical here the coordinates is rho, phi, z. You know that rho is the r of polar coordinate and phi is the theta of the polar coordinate, so they will transform accordingly. So it is rho phi plus pi minus z. spherical polar, here the coordinates is r, theta, phi, and you know that this phi is actually theta polar coordinate, so these two transformation is known. So this is r, phi plus pi, and it remains theta. If we go on mathematically, we know that x under our parity operation is r sine phi prime cos phi prime, y is equal to sine now since we have written it in this fashion, so this is negative, r does not undergo any change, so sine theta prime must not change its sign. On the other hand, cos theta prime must change its sign, so it should lie in the second quadrant. From this we write it as pi minus theta. Let me check it physically. So if we have, this is the coordinate position vector r, and it is the minus r. So this angle is theta. So under parity, the angle becomes this much. So this total angle is pi. So this much is pi minus theta. That has been written over here. So this is the conversion of coordinates under parity operation. Now we shall consider a two-dimensional case, that is a function f of x which is being operated by the parity operator, and what happens to the consider f of x, such a function f of x. If we operate parity on f of x, we will get f of minus x, because parity operation changes the value coordinates. So p square operator, square of an operator means that it operates twice. So this is p operating on p of f of x, which this part we know that this is p of f of minus x, and when this p operates on it gives you f of x back. This is one way of looking at the problem. An alternative view. We use the eigenvalue equation of the parity operator. So we write eigenvalue equation for the parity operator. P operating on f of x gives you lambda times f of x. P square operating on f of x gives you p operating on phi of f of x. This part is lambda f of x. Lambda being a scalar constant is not being operated by p, so this is lambda. P operator operating on this, so this is lambda square f of x. If we compare these two equations, we see that lambda square is equal to 1, or lambda is equal to plus minus 1. That is to say, if we consider this, P operating on f of x gives you f of minus x. This is equal to either plus f of x or minus of fx. When the sign is plus, we call it even parity, and when it is minus, it is called odd parity. If we consider a function which has even parity, then when we expand it in Taylor series type function, such function will have f of x is a0, a2x square, a4x to the power 4. Only even power will appear, and for this it will be a1x plus a3x cube plus so on so forth. Only the odd power of x will appear. Now we come to the Hamiltonian. This is the eigenvalue equations of the parity operator. So whenever f of minus x is equal to plus of x, we can say even function, that we have consider the solution involving cos part, and when the negative sign appears, it is the solution involving sine part. Now we see what is the effect of parity operation on the Hamiltonian. The Hamiltonian for this system, system that is for one for 1D infinite rectangular symmetrical H. This is the H of x actually. What will be H of minus x? H of minus x is minus h line square by 2m d2 d of minus x2, which is equal to minus h line square by twice m d2 dx2. This is equal to Hamiltonian at x. So Hamiltonian this Hamiltonian is not affected by the parity operation. In fact, any Hamiltonian for which v of minus x is equal to v of x does not undergo any change under the action of parity. Example of such potential is this is the zero potential or a constant potential, or in general half kx square harmonic oscillator potential. Such potentials are have this property. But on the other hand, if we have a potential of the form ax, this does not belong to this category. Now we consider the commutator of Hamiltonian and parity. And it operates on a wave function x. Writing explicitly, it is H operator, P operator operating on psi of x minus P operator, H operator operating on psi of x. Now, when P operates on this gives you H operator psi of minus x. This part. And this part gives you h when h operates on psi gives you e psi. So this is minus p operator e psi, and then it is being operated by this. Now you have seen that h does not undergo any change by changing x by minus x, so we can write it at h of u psi of u, where u is equal to minus x, and for this we write and this is the conclusion is HP commutes if v of minus x is equal to v of x. So for such potential, symmetric potential, h and p will have simultaneous eigenfunctions. So the conclusion is potential h and p as they commute will have eigenfunctions. That means an eigenfunction of h will also be an eigenfunction of p, and the vice versa. The eigenfunction of p is either even parity solution or the odd parity solution. And we found that the solution of Hamiltonian separates into two categories. One belongs to even category, another belongs to the odd category. Such thing will continue all along the quantum mechanics. When the potential is the symmetric one, the parity or the solution will have a definite parity. Another very famous example that I forgot to mention is the Coulomb potential, 1 by r potential. Since it depends only on the scalar r, by parity operation r remains the r, so the potential is symmetric with respect to the parity operation or invariant under parity operation. And the solution, when we shall work out the solution of hydrogen atom problem, we will see that it will have a definite parity. And this is by studying the symmetric potential well, we have got some extra information. The extra information is that the solution have a definite parity, and the ground state belongs to an even parity state. That has to be, because if we the ground state belongs to an even parity means if we change x by minus x, the wave function does not undergo any change. And this is, on the other hand, is the most stable state of the system so far quantum mechanics is concerned. Even in the ground state, due to thermal agitation, the particle oscillates about its mean position, and whenever it goes to the from the right of the middle to the left, the x changes. Had the wave function belong to an odd parity state, then the wave function will change sign. So some physical quantity related to the system will also undergo a change, and that will cause an instability in the system, and that cannot be a stable state. So for the ground state, we must be a stable one, that is by changing x by minus x, nothing changes. So as though a function that does not undergo any change, any other quantum mechanical variables, so far its expectation value or the eigenvalues are concerned, does not undergo any change. So this is a great information that will help us a lot in future for more complicated problems.